Hello everyone, welcome back to DTS Programming. My name is Daniel and today I'll be presenting my project binary search tree for my CSC382 course, Data Structures and Algorithms at the University of Advancing Technology. For this assignment, we basically just had to create a binary search tree program that would allow us to manipulate that search tree in different ways. The expectations here, as you can see, insert nodes, delete nodes, find maximum value, and traverse the tree. And then there were some bonuses for performance analysis and self-balancing, but I was unfortunately unable to get to those bonuses. But I will be implementing those at a future time for my uh, own learning and because I was really hoping to make a self-balanced tree. But anyway, getting into the program that I created. Here we start with the main menu, and I have options to manually enter tree nodes, to randomly populate an entire tree, to display tree traversal, to find a node value, and to delete a node. And then of course my exit option. For this presentation, I've actually predefined a little tree model that I'll be using to explain some of the methods later on. So what I'm going to do is go ahead and build this tree. And you can see that this tree is off balance as it is, which is why I'd really like to implement self-balancing. But I'm out of time on this project, so I was unable to do that. As you can see for this tree, it has no right nodes from the root, but I can still demonstrate the methods uh, even as it is right now. So it looks like we have 9 nodes here. 56, 50. Let me go ahead and verify that I didn't miss any. Okay. So there you were able to see that I was able to manually define tree nodes. What I'm going to do next is I'm just going to show my delete node. Um, and so the way I have this set up is it automatically displays the in order traversal so that I can see the nodes that are available in my tree. Of course, if this was a larger tree, much larger, then I would not have this. I wouldn't want to display 1,000, 100,000, a million nodes. So I'll just randomly pick a value. We'll go ahead and delete 36. There you go, node 36 has been removed. We display the traversal again, and you can see that 36 is no longer in my tree. Delete another node. I will not. And then I will go back and put that node back in. So if we go to the tree traversal, we have a sub menu here, which allows us to choose in order, pre-order, or post-order. So we'll start with in order, and you can see that the in order traversal is from left to root to right. And I also went ahead and automatically added in the smallest and largest to show my maximum and minimum values. So smallest node is 21, largest is 56. And we can do that for any traversal method. Pre-order from root to left to right. Root node is 56. You can see my diagram on the left. And then again, the smallest and largest node displayed. And finally, my post-order traversal, which is left to right to root. And you can see that that is also correct. All right, we will go ahead and find a node value, and let's enter 42. There it is, 42 currently exists. Simple enough. If we go and try to find a value that doesn't exist, very clearly states that node is not in the tree. There's my program so far, and I'm going to go ahead and exit and run it one more time. I did not create any methods for deleting the entire tree or creating multiple trees, and so when I want a new tree, I just restart. If I were to add more nodes, even using random, it would add them to the current tree that I just created. So I just want to show that the random functionality. Please enter the number of nodes you would like to generate, say 10. And then I added code that would allow me to check the time elapsed, that this was part of preparing to do the analysis on my program, depending on the number of nodes I was adding and eventually the number of nodes that I would be removing. So you see the time there, 0.0008617 for 10 nodes. And we can display those nodes so we can see 10 nodes were created. The smallest was 10 and the largest is 101. And as part of the assignment, there were specifications to check the amount of time for adding 100, 1,000, 10,000, and 100,000 nodes, which is why my program does have the code showing the time values. So we can do 100, 0.000.562, 10,000. There you go. You can start to see that time come up. And one more time. That's 1 million nodes getting added. And I tested this prior, so it's I know it would take a while, but I knew it wasn't going to break. So there's the time elapsed to add 1 million nodes. And of course, if I went and displayed that tree, I imagine the program would break and I would have to stop this video. So I'm not going to do that. So from here, we're going to go ahead and check out the code. I'll try to run through it relatively quickly. What I have is my main program here. And I have a tree node class and I have a binary tree class. So in my main program, then I have my various methods for my program class. I have my main menu, a method to verify the menu options when it is put in by the user. Call menu sends the program to the right method to run after that point. Manually define tree nodes, create random tree, generate random non-repeating list. That's for my random tree. My tree traversal, find a specific node value and delete nodes. So let's expand this out and look at it. Main menu is simple enough. Our main, it just calls the main menu. Everything else will run from there. My main menu, of course, display my options. Once an option is selected by the user and stored here in option, then we'll pass that into the verify menu option method. Verify menu is just error checking, basically making sure that the option passed in is a number. If that option is not a number, then they'll get into this while loop and it will prompt them to enter a numeric value and I do all the conversions from string to int, and then it checks if the value is between my menu options 1 and 6. If not, it will recursively call this to check whatever new value they put in. And then it will call the call menu option method and pass in that converted input. And all call menu option does is a switch statement based on the option they pick. It sends them to the method that correlates with that option. So here in my methods, manually defined tree nodes, we store some values: int node value and node count, string for a yes no option, and we set it equal to y, and a boolean value exists set equal to false. And here we create a integer list called nodes. After that, we drop into this while loop. While yes no value is equal to y, then we will clear the console screen so that all of this doesn't fill up with every iteration. We'll go ahead and display a header, prompt for a node value, and we will store that value into our variable. It's a int variable, and so we convert it from string. So we do the int32 parse on our console read line. Then what we're going to do is a for each loop to go through all the values in the nodes list. So for each node in nodes, if the node value is equal to a node, so if this value passed in is equal to anything that's in the list, then the value exist is set to true. And for our first loop, there will be nothing in this. So it'll just kind of skip over all of this, but next time around it will check and verify. So if the value exists in the list, then we'll notify that that value is already in the list. Value exists will be set back to false. Otherwise, if the value is not in the list already, then we will just go ahead and add it to the nodes list. And then we'll prompt if the user would like to add another node, and if they say yes, this will loop again, and it will continue to do that and add numbers to that list. Once the user has added all the numbers that they would like, then it will display this new nodes added. And then we'll do another for each loop for nodes, node in nodes. So it's going to go through, it's going to iterate through the list again. With each iteration, we're going to increase our node count. Here we're going to call our add node to tree method from our binary tree class. And we'll pass in the value of whatever current node for each iteration. And then we'll display the node with the node count and the value of that node. So if we go over here to add node to tree in our binary tree, and here in our binary tree class we have a private tree node instance called root, and we have a constructor here where we set our root equal to null. In our add node to tree method here, we check if the root is not equal null, and we call root.insert and pass in the value, and this root.insert is in my tree node class. So we'll call the insert method from my tree node class on root. We'll get back to that here in a second. Otherwise, if the root is null, then the root value just gets set to a new tree node with the passed in data. So here, if we go to our tree node class and look at the insert method, And in our tree node class, we have some member variables here. We have an integer called data with getter and setter, and tree node objects called left child, right child. We have our constructor, which sets data to the passed in data, and it sets the left child and the right child values to null. Then an insert. If the passed in data is greater or equal to its current data, which is the root data at this point, then if the right child is equal to null, meaning there's no right child, then the right child will get set to a new node with the passed in data. Otherwise, if there is a right child, then that right child will recursively call this method, and it will loop back around starting from this right child. And basically what that's doing is it's going back around and it's checking the value is still greater than the node. If the value is greater than root, then we want to go down to the right side. If the right child is null, we're going to add the node. If the right child has a value, then we're going to just call this again and keep iterating down to the right until a node is found that has a null value for the right child, and then we'll add that node. Otherwise, if the value passed in is less than the root value, then we'll do the opposite. We'll check if the left child is null. If it is, then we'll add a new node. Otherwise, we will continue to recursively call this method and go down to the left until we find a place to add a new node. So once that's done, this will add all the values from the list and create a node for each. It will display all those nodes, and then it will return the user back to the main menu. Moving on to create random tree. Again, we're going to clear the console. We're going to store the number of nodes, display what's going on. This is the random tree generator. Prompt for the number of nodes that the user would like to generate, and then store that into this variable. And then we call the generate random non-repeating list and pass in the number of nodes. And so that is right here. And so here you see we have a stopwatch instance called SW. That's to do my analysis check. Then we create a integer hash set called node values and a random object called rand. And then while our node values count, so our hash set, the count of our hash set is less than the size, the value passed in for how many nodes we want to add to our random tree, then while this number is less than the size of our tree, it will iterate through. Say our size is 10, it'll go through 10 times and generate a random number between 1 and 110 every time. Right here we'll start the stopwatch, and then we'll do a for each loop through all the values in our hash set, and we will call our add node to tree method from binary tree, which we just went over, and then stop the stopwatch. After that, we'll display how many nodes were added, how much time that took to execute, and then return to the main menu. In tree traversal, clear the console, store a choice value. Here we have our submenu. we'll prompt to find out which traversal method the user wants to display, and we will call the traversal method from our binary tree class, and we will also call our get smallest and largest from binary tree. So we'll go over these two methods, traversal and smallest largest. Here in our traversal, we check if the root does not equal null, then we offer a switch statement passing in the traversal choice from the user. If they choose 1, we'll display the in order traversal sequence, and then we will call in order traversal from our tree node. And for the other cases, we will either call pre-order traversal or post-order traversal from our tree node class. And for get smallest and largest, again, if the root does not equal null, then we will call smallest node and largest node from our tree node class. Otherwise, we will notify that if the root is null, the tree does not exist, and we will notify the user that they need to create a node. Going to our tree node, you see our 3 different traversal methods, very similar with just some slight variations. So this is called from root. It is going to check if the left child does not equal null, then it will recursively call this method from the left child so that it will continue to the left to see if the left child is null. So until it gets to a leaf node that has no left child, it will continue this recursive loop. Once it gets to that leaf node, the far left value, which would be the lowest value, it's going to print that data. Then it's going to check if that node has a right child. And so this is actually where I brought my diagram. So just showing that, starting off in order traversal, if the left child does not equal null, so we have a value here, it's going to call the traversal again from this value, and then it's going to check, is it null? Is it null? Is it null? On and on until it reaches a node where the left child is null. Then it's going to print that data. Then it's going to check if the right child is null, and this one does not have a right child, so then it's going to go back up the tree. Going to check again, is right child null? There's no right child. Or if the right child is not null, so does the right child exist? No, it doesn't. Here, does the right child exist? Yes, it does. So it's going to go here. From here, it's going to recursively call the method again, and it's going to start back at the top. So it's going to check the left child again. So it's going to go from here to here to here. Once it sees there's no left child and no right child, it's going to start going back up the tree until it gets back to here. Then it's going to go to this value and print it, and so on until it gets all the way back up to the root and all the left and right nodes have been checked. I really had to create a diagram to solidify my understanding of how this worked. Pre-order is very much the same. The difference is the order of how it prints. So right when it comes in from root, it's going to print the data. So when you do the pre-order traversal, it's root, then left and right. So it will come in, print the root, check if left child is not equal null, and do the same as the other one. It's going to go all the way through, and then it will do all the left values and then all the right values. And post order is very similar, except it goes through left and right, and then the root node gets printed last. For smallest node, largest node, these are kind of similar, but very simple. What they're going to do is, I have a minimum value set here. This is going to come in from root. It's going to check if the left child is null. If the left child is null, meaning there's nothing over here on this side, which means our root is the lowest value. And so it's going to set this minimum value to this data, which is root when we first come in here. And it's going to display that value. Otherwise, if the left child is not null, then this is going to recursively call this method and go down to the left until it reaches this node that left child is null, and then it will store this into our minimum value. And largest node works very much the same way. Got a max value that we're going to store. If the right child equals null, meaning there are no right children, then the max value is the root. So we're going to set it and then display it. Otherwise, if the right child is not null, then we're going to recursively call this method and go down to the right. If there were nodes over here, this would go down to the right. Let's say this is our root. It's going to go down to the right until it reaches this final node, this leaf node, which will be the largest value in our tree. Pretending these aren't here. And then when it reaches that node where the right child is null, then it will set that data value and display it. So after it displays the traversal method and the minimum and maximum values, it will go return back to the main menu. In this method, we find a specific node value. We're going to clear the console. We're going to store the node value. We're going to prompt the user to enter the value they would like to find. Then we're going to call the find tree node from our binary tree class and pass in that value. In binary, we go to find tree node, check if the root does not equal null, and we call the find method from our tree node class. Otherwise, we display that the tree is empty and a new node needs to be created. In our tree node, for our find method, we check if the data is equal to this data. So if the passing data is equal to the root data when we first come into this method, then we'll display that the value of the passed-in data already exists in the tree. Otherwise, if the data is less than the root data, or I should say the current data, current node that we're at, and the left child does not equal null, so the passed-in data is less than the root, it's going to go left, and the left child exists, the root has a left child, then we're going to recursively call this method until we reach a point where the data is equal to, the passing data is equal to the current data of the node that we're searching for. Similarly, if the data is larger than the current data that we're at. And let me use this again. So if the data that's passed in is larger, and the right child does not equal null, then we're going to move to the right and check if the data value matches this next node, or we're going to keep moving to the right to see if the data matches the next node. Otherwise, if the right and left child is null after we've gone through the whole tree, then we will notify the user that the value does not exist in the tree. So if this goes all the way to the left, all the way to the right, doesn't find the value that we're searching for, then we will notify the user. Finally, for our delete node, and this is the fun method here, this is the most exciting part of our binary tree. Before getting into self-balancing trees. So again, we have a yes/no value set to y, a node value to store passed in node. While loop, while our yes/no is equal to y, clear the console, show that we're deleting a node. We're going to call the traversal method here, and I passed in, I just hard coded the 1, so it's just going to display that in order traversal, so you can see all the nodes that are available. It's going to prompt for the node to delete, convert that to an int, and then call the remove tree node from our binary tree class and pass in the value to be deleted. And then we're going to run our traversal method again and display all the nodes with the deleted node now gone, and prompt if the user would like to delete another node. So let's move to our remove tree node method in our binary tree class. Coming in here, we set a tree node object called current, and that is set equal to the root. Tree node parent, and that is also set to the root. And then a boolean called isLeftChild, and that is set equal to false. And that will just check if there's a left child or if we need to go to the right. We'll show that here in a minute. So we check if our current is equal to null, then we're going to write display to the console, tree is empty, create a node. So current coming into this method is our root. If root is null, create a node. Simple enough. Then we go into this while loop while current does not equal null and the current data does not equal the data that's passed in, meaning the root node is not the one being deleted. Then we will set parent equal to current, so currently parent and current are both this root value 56. So we'll set parent to current, so this is now parent. Then if the data that's passed in is less than the current data, then we will set current equal to the current left child, so this current becomes this is now current, and then we set the isLeftChild boolean to true, because this is the left child. Otherwise, if the data passed in is greater than the current, then we're going to set current equal to current right child, and isLeftChild will be equal to false. So if this was greater, we would go this way, and the isLeftChild boolean would remain false. And so we will keep doing that while current is not equal null and the current data does not equal the passed in data. So this will continue to go down to the left or to the right until it reaches a leaf node or until it finds the value to be deleted. Alright, after that, if current equals null, then the node cannot be found in the tree. It's gone through the whole tree. Current is equal to null. We've reached our leaf node. We didn't find the value. This is where we're checking if the right child and the left child is equal to null. So if our node to be deleted, let's say is 21 now is our current. That's our node to be deleted. It's going to check if the left and the right child are equal to null. Nothing to worry about there. If our current is equal to root and it has no left and right child, that means the root is the only node, then we just set it to null. Simple enough, there's no tree there basically. Otherwise, if the current node is not the root node, which is the case here, if it is a left child, which it is, so is left child is set to true here at this point, then the parent's left child is set to null, which is our current. So that basically severs that connection there. And so that node will be effectively deleted and picked up by garbage collection. If it's not a left child, say we're over here, then the parent's right child would be severed. So leaf nodes are the easiest. They don't have any child nodes to worry about. Moving on to the next case, if the current right child is equal to null, meaning our node to be deleted doesn't have a right child. If the current equals root, then the root is set to the current left child. So in this case right here, if this was our node to be deleted, it has no right child, so the root would be set to its left child. Otherwise, if it is not the root, if it is a left child, like this, so let's say we're deleting 36. If 36 is a left child, which it is, then the parent's left child is then set to the current's left child. So this will get attached. 42 will get attached to 21. Otherwise, if it's a right child, then the parent's right child will get attached to the current's left child. So if the current node is being deleted, let's say it's this one, and number 49 doesn't exist. If the node to be deleted is a right child, then the parent's right child will get attached to the current's left child because there's nothing over here, so this will get attached to this. See where diagrams start to help immensely. Alright, here's a similar case. If the current left child is null, meaning there is no left child, but there is a right child. So let's say 49 had a node here. Say that connection existed. Current left child is null. There is no left child here. If current is root, once again, then the root will get set to the current's right child. This left child is null. So if this was the root, then the root would become this node. Otherwise, if it's not a root node, then it will check, is it a left child? In this case it isn't, but if it was, then the parent's left child would get set to the current's right child. So this connection would be made down here to a right child. Otherwise, if it's a right child, then the parent's right child will get set to the current's right child. So just make the connection like that. Alright, moving on to the most exciting case. And this is if the node that we're deleting has a left and a right child. So here we can clearly see that either here at 42 or 47. We'll go with 42. So we'll say here the node being deleted has a left and right child. What we're going to do is we're going to make another tree node object called successor. And we're going to call another method called getSuccessor and pass in the node to be deleted. So let's go look at that. Here in getSuccessor, we are going to create a tree node object called parent of successor, set that equal to the node that's being deleted, the passed in node. We're going to create an object called successor, set that equal to the node to be deleted. And we're going to set a tree node object called current equal to node's right child. So this will be current, and this is currently parent and successor. So we'll check while the current does not equal null. So while this blue square is not null, then the parent of successor equals successor. So this now equals successor. Successor equals current. So this will become our successor. This is our parent. We'll just keep the parent white. And successor equals current, and then current equals the left child. It's current. And so that while loop will loop until current is equal to null. So it's going to go through again. Parent becomes successor. This becomes parent. Successor becomes current. And current becomes current's left child. And then it's going to loop one more time because current is still not equal to null. Parent becomes successor. Successor becomes current. And then current is current's left child, which is null. So current is now equal to null. And our successor value is 43. So essentially what happened here is our node to be deleted has a left and a right. And so what we did at the very beginning, we went to the deleted node's right child, and then we iterated down to the left to find the lowest value that's higher than our node to be deleted. So we go to the right and then all the way to the left, and that's the value that will replace our node to be deleted and maintain the structure of the tree. So after we run that while loop, we check if the successor, this value, is not the node to be deleted's right child. So it's not this one right here. So if the successor does not equal the node to be deleted's right child, then we're going to check if the parent of successor's left child, which is our successor, equals the successor's right child if it exists. In this case it's null, so that condition does not need to be made. Otherwise it would set the left child value to whatever, if there was a node here, which would be higher than this but lower than this. So it would make that connection like that. Then our successor's right child is set to the node's right child. So this right child gets attached to 47, which is the node to be deleted's right child. So this right child is set to the node's right child. So that connection is made. And then the successor's left child will equal the node's left child. So this will be attached to 36. This will be attached to 47. And then we will return that successor value, which is 43. And then we'll go back into our delete. So now what we have here is we have our node to be deleted. It still has these connections, but they also are connected here. So it's kind of a loop. This is the left and right child of 43 currently, but they're still the left and right child of 42. So it's kind of like a big circle. which is obviously not what you want to have. So once we go back into our final section of our delete method, then we got the current successor. We're going to check if the current, which is the node to be deleted, so we're back to if the node to be deleted is the root, which it is not, then the root is set equal to the successor. So then this becomes the root. So essentially is moving that into place. Otherwise, if the node that's going to be deleted is a left child, which it is, then the parent's left child of 50, is set equal to the successor. So this gets severed here, it gets attached here, and this is already attached to 36 and 47. And so essentially 42 is out of there and all the connections are properly made. Otherwise, if the current is a right child, it is not in this case, then the parent's right child becomes a successor. So if there was a node here, then its right child would be our successor node. So all those connections would still be made. And then we display that the node has been deleted. So just to recap, we passed in this node to be deleted. Then we saw that it had a left and right node. We called the getSuccessor method, which first iterated to the right and then down the left side of that right tree to find the lowest value of that tree, which is still greater than the node to be deleted, but less than this node here and greater than this node here. And then once that's done, we set the left and right child to these two values here. And then we come back in here and we check, is the root node to be deleted the root? No, it's not. Is the left child? Yes, it is. So we set the parent's left child equal to the successor node. So that connection is made from there to here, and these connections are already made here and here, and effectively our node has been severed. And so I believe that's the whole program. We were able to manually define a node, a tree, randomly populated tree, go through the various tree traversal methods, find node values in our tree, delete nodes from our tree. And so that has been my project for this week, to learn all about binary trees. Eventually, like I said, I want to get into self-balancing trees so that my tree, if it's off balance like this, it will rotate and become balanced. That way it will maintain that big O of, I believe it's big O of log n, and it will be more efficient when traversing, finding, adding, or deleting nodes. So that has been my project, Binary Search Tree, for my CSC382 class, Data Structures and Algorithms at the University of Advancing Technology. Thank you.